Well, it looks like we can start. Welcome back. Looks like it'll be a small class today, but that's understandable. Next week we're on holiday, and usually the last class right before going on a break is a tough one to attend. So I appreciate you folks making it in, and even if you're watching this on YouTube later on, you're still here in spirit, in my opinion. Any questions at all, folks, to start us out today? Okay, well, today's class, we're going to be talking more about eigenvalues, eigenvectors. Section 5.2 is going to show us how to actually obtain eigenvalues for a particular matrix A. And we'll probably go into section 5.3 just a little bit as well, since 5.2 is actually a pretty short section out of nowhere. I think the author could have combined 5.1, 5.2, but that would have just made it a little bit too big. So this is just the excess of what's going on in section 5.1. So that's what we're going to be working through today. Notice the due dates also for everything that we've been covering this week is all in December. So nothing's going to be due on Thanksgiving break. That sounds kind of awful. So these due dates are going to be due right after we come back from the holiday. Well, not a whole lot of announcements today. Any last questions, folks, before we get started? Okay, before jumping into 5.2, I think it's beneficial to kind of just warm up a little bit by looking into very briefly what we did in section 5.1. We did a lot of things, but the two main things are the definition to start. This is what it means to have an eigenvector x and an eigenvalue lambda. We have to have a square matrix to start. So some of the concepts do fit into the invertible matrix theorem. And if matrix multiplication just turns into rescaling the input vector x, then we say we have an eigenvalue. The critical thing is this particular equation can only work when x is not zero. So when it is zero, lambda, any lambda would work. It's interesting when it's a non-zero x. So that was our major core definition that we started out with. Then coming down below, we had this concept. If you took that original equation and just rearranged it, you would say that lambda is an eigenvalue of an n by n matrix A if and only if A minus lambda I times x has a non-trivial solution. That non-trivial solution is the x not zero, the eigenvector that we mentioned before. Welcome to class. We were just mentioning the start of the announcements that it's going to be a pretty small class, but we'll get through it. Usually this one's hard to attend right before the break, so it's totally understandable. Well, the next idea, the big one that we're going to connect to the next section is when you said A minus lambda I times x equals zero has a non-trivial solution, you can just go right into the invertible matrix theorem. I've got it preloaded here. And connect that theorem all the way down to the bottom here, parts T of the invertible matrix theorem, and say the determinant has to be zero. Non-trivial solution means this part's false, where it says only the trivial solution. So since that part's false, and because this is a square matrix, even if we subtract lambda times I, this whole thing is still square, we go down here and negate this statement and say the determinant of A minus lambda I is zero. So that's pretty much the key. We use that equation right there in section 5.2 to actually find the eigenvalues. So that's the quick tour of concepts so far. Any questions at all, folks, about 5.1? Anything in particular? Okay, so pretty much the next section, 5.2, starts right here. We call this the characteristic equation when there's an actual equation. For focusing on just the determinant part, we call it the characteristic polynomial. So going back to section 5.2, we have that same relationship, which came from the theorem and the corollary. The scalar equation determines A minus lambda I is a characteristic equation. Solving this will give us our eigenvalues. A is an n by n matrix. And if you focus on just the determinant parts, that's the characteristic polynomial. And that polynomial will have degree n. which is an important thought to think about at the moment. If this is a degree n polynomial, the moment you set it equal to 0, out of nowhere, here comes the fundamental theorem of algebra. It has something to say about that. So let's make a comment right here. By the fundamental theorem of algebra. It's kind of fun when these things pop out of nowhere sometimes. Because we have a degree n polynomial, determinant a minus lambda I equals 0 has exactly n solutions. You have to be specific with what you mean when you say n solutions. They might not all be distinct, so these would be repeated according to their multiplicities. And this is part of the reason we were starting to talk about multiplicities in the last section. So let's put in that qualifying statement to make this all true. Exactly n solutions, repeated according to their multiplicities. So this tells us any square matrix whatsoever, if it's n by n, you will find n eigenvectors, or excuse me, n eigenvalues. Some of them might be repeated, but they will be repeated according to the multiplicity, and you'll fill out exactly n of them. So no matter what matrix we put down, those eigenvalues are somehow characteristic about that particular matrix. Well, that's what the theorem is below saying. This theorem is just what we penned in, the fundamental theorem of algebra. And the theorem below tells us lambda is an eigenvalue of the n by n matrix A if and only if it satisfies the characteristic equation. So that's where we start, kind of what we were hinting at in section 5.1. Solving that equation right there by the red dot generates all of our eigenvalues, which means it could be a tough equation. If we have a 3 by 3 matrix, you might know that solving a third degree polynomial sometimes requires a couple little bits of ingenuity. There is a, say, an analog of the quadratic formula to degree 3 extends to degree 4, but they've proven that there's no such analog at higher and higher degrees, which is kind of amazing as well. So finding the eigenvalues is not always easy, but we know they are out there, they exist. So let's start off with the 4 by 4 matrix. On its face value, if I give you a random 4 by 4 matrix, that's a really hard problem. You might have to use numerical methods, say Euler's method, to approximate these solutions. But there's a lot of zeros here, kind of almost strategically put in to allow us to actually solve this without having to use a whole bunch of extra tools from calculus and algebra to actually get the roots. So example 1, part A just says, find the eigenvalues of A. We go immediately to the characteristic equation, determinant A minus lambda I is 0. This operation we mentioned in section 5.1 is only going to operate on the main diagonal of A itself. So across the main diagonal, all we're going to be doing is subtracting lambda from those 4 values. And usually, instead of putting equals 0, let's just manipulate this, solve the determinant, and then at the very end step, we'll write equals 0 and solve the polynomial equation we get. So now this is a determinant going 1 minus lambda zero, 1, 1, 0, then 1 minus lambda again, 0, 0, then 0, 5, 2 minus lambda, 0, and finally 0, negative 10, 0, 3 minus lambda. Okay, we've got it. So there's our new determinant we're about to take. Really, now it's just kind of a review of what we did in chapter 3. But one thing that's kind of sad about this is chapter 3 did give us a lot of nice tools to work with. Let's take a look at some of them. Some of them do come up in a nice way. Here's some nice properties of determinants from section 3.2. We'll be using some of these in these notes. But what's no longer nice is good old theorem 3. Theorem 3 told us that we can often, very, very often, simplify a determinant in a humongous way by doing a row replacement operation. This part right here highlighted in yellow. But it falls completely on its face with this kind of determinant. Because there's a variable in every single row, any row replacement operation I do is just going to spread out lambda into more and more entries, and sometimes in more and more complicated kind of ways. It turns out row operations inside this determinant only makes it worse in about every single situation, and that's pretty unfortunate when you think about it. So usually when you get these kind of determinants, the only thing you can really do is just work it directly. We'll just hope there's enough zeros in strategic locations, like in this problem, so that it's not a tough problem. It'll be solvable by hand. Otherwise, it's a numerical analysis kind of problem. Looking at this matrix, if we do a cofactor expansion across row 1, that's probably the most ideal way to do it. It has the most zeros, 3 in total. Or I guess there's a tie. You could go down column 2 if you prefer for the same kind of work. But definitely try to do this as strategically as possible. I think going across row 1 makes the most sense. It's the most direct approach on this. So let's do that cofactor expansion. First, you'll get 1 minus lambda with a positive sign. Multiplying a reduced determinant, delete column 1, row 1, and carry in this submatrix determinant. 1 minus lambda, 0, 0. By 2 minus lambda, 0. Negative 10, 0, 3 minus lambda. Okay. Now, this is a nice determinant to take. This is, at this stage, upper triangular. And this is a fantastic property of determinants and eigenvalues at the same time. If our original matrix was upper triangular, we would have known the eigenvalues. But there's non-zero stuff below and above. This is neither upper or lower triangular. It's definitely not diagonal. But this one is. The determinant is now the product of the main diagonal. So we can say this equals 1 minus lambda times this new entry, 1 minus lambda. That just squares it, bumps the power higher, times 2 minus lambda times 3 minus lambda. And now it's set equal to 0. So if we're looking at just this part right here, before the equals 0, that's the characteristic polynomial. But including the 0, this whole thing is the so-called characteristic equation. Solving this characteristic equation is going to give us the eigenvalues, but it's basically solved the moment you start to look at this. This is a complete nice factorization, just a fluke of how this matrix is working. So we can just read off the values. This implies lambda 1 is 1, lambda 2 is 2, third eigenvalue, lambda 3 is 3. Organization is going to be a big part of what we are going to be doing in section 5.3. So I'll be careful with the subscripting. It's good to have a tag or a name for every single eigenvalue you're working with, just to keep things straight, particularly for the next section. So we found the eigenvalues. We'll state the multiplicity of each eigenvalue. For the bottom two, eigenvalues 2 and 3, they came from a group with powers 1 on both. And so these both had multiplicity 1. The top one came from a power 2, so this one has multiplicity 2. So that's pretty much the finalization of part A. This is how we get the eigenvalues. Multiplicities are going to play a bigger and bigger role as we go. So looking back on theorem n, theorem here, the n by n was telling us we would get exactly n eigenvalues, but they would be counted according to their multiplicities. So we have multiplicity 1 plus 1 plus multiplicity 2. If we count up the sum of the multiplicities, it would be equal to 4, as it should be, because our matrix A was of size 4 by 4. So if we were, say, only summing up to a multiplicity of 3, something's gone completely wrong. The theorems wouldn't have been wrong, but something strange must have happened in the algebra. Maybe I just didn't copy something down. Well, we did, folks. That's our eigenvalues. There's a part B to this, but any questions so far? Okay, let's take a look into the next one. Part B comes with a theorem out of nowhere. That's kind of jarring when they look at that. It's an important theorem, but let me see if I can kind of box it out a little bit better. This is a theorem from section 4.5, which is really, really valuable to us. The one with multiplicity 2 is kind of interesting. If the eigenspace of this one has dimension 1, it tells us something particular about that matrix. In the next section, we're going to call it defective. And if this came from an applied setting, that's a oh crap kind of moment for the engineers who might have been working with this. This is going to cause lots of problems, lots of complications. If this matrix described, say, forces on a real structure, it'd be bigger probably. But if that described forces on, say, a bridge, and it came out defective, we would say the bridge is probably defective as well. So there's lots of interesting things that eigenvalues are trying to say with dynamical systems. So we want to see what is the dimension of the eigenspace corresponding to the highest multiplicity one. We hope dimension 2. But you don't have to work by finding the actual null space to this. You can use just the theorem from section 4.5. The dimension of the null space is just going to be the number of free variables in the equation ax equals 0. We have a slightly different equation, but it's going to be the same concept. When it says eigenspace corresponding to lambda 1 equals 1, we mean null a minus 1 times I, where the 1 comes from that eigenvalue. So we need to know the dimension of that eigenspace. But when we go to solve the dimension of that eigenspace, that's just going to be the set of all vectors x such that a minus 1 times I x equals a 0 vector. So essentially all we're doing is returning to the homogeneous system right here. Let me take a quick screenshot of the original matrix A. Now let's go to solve what this is going to be just in terms of free variables, not actually building out the full null space. Okay, I think I've got enough space. I'll just put here a note, continues. So we're solving a minus 1 times x equals 0, and we would get this matrix. 1 times I is just going to go to the main diagonal and subtract 1 each time. So we'll get a 0 here, then 0, 1, 1, then 0, and 0 again when we subtract from this entry, and then 0, 0 below, and so on. So it's going to be 0, 5, subtract 1 for this entry here, which was 2. Now it's a 1. Let me fix that. And then 0, 0, negative 10, 0, and finally a 2 in this position. So minus 1 times I just means subtract a 1 from here. It's augmented with the 0 vector. And we'll just do enough row operations so we can determine, I guess that's kind of stuck up there. We'll do enough row operations in order to determine what the free variables are in the system. Needed a little bit more room. Let me carry this down. Okay, I think we're done with that matrix A. We don't need to do too many row operations, it looks like. Maybe first thing we can do is bump up maybe row 3 or row 4, really same difference either way you'll go, up to row 1. So I'll bring this one to the top. 1, 0, 0, 2, 0. We're only going for an echelon form. I'll make this my row 2. 1, 0, 1, 0, 0. This can be row 3. 0, 0, 5, negative 10, 0. And that's got to be our row 4, the zeroed out row. So we have a pivot right here. We need to eliminate that entry right below. So that should take us not too much time. First row 1 is 1, 0, 0, 2, 0. Once again, multiply row 1 by -1, adding it to row 2 will give us 0, 0, 1, -2, and 0. Then looks like we're pretty much done. We have 0, 0. Oh, hang on, not quite done. It's not yet in echelon form. One more operation. 0, 0, 0, 0, 0. If I thought enough ahead, I might have divided this row by, say, -5 to make it a -1, +2. But either way you look at it, this row is going to be eliminated. We can multiply row 3 by -5, add it to row 2, and it wipes out both of those entries. So now it's row equivalent to 1, 0, 0, 2, 0. Here's the reminder that we augmented. 0, 0, 1, -2, 0. And everything else has been completely wiped out. Okay, so let's take a look at the variables. We have x1, x2, x3, and x4. When we identify the pivots, we see that x1 is a basic variable, x3 is a basic variable, but two of them are free variables, x2, x4. We go back to theorem 4.5, a really powerful theorem, and we can just say two free variables, namely x2, x3, implies the dimension of the null space of A minus the eigenvalue 1, the one with the higher multiplicity 2, times I, is 2. So if we filled out by, or continued by filling out what the null space is, it'd be the span of two linearly independent vectors. Those vectors would be the eigenvectors themselves, but all we want here was the dimension. And it gives us some comfort. If this was a really important matrix in an implied setting, it tells us this original matrix at the very top is not defective. We'll get an eigenvalue from 2, we'll get an eigenvalue from 3, and because the dimension was 2, we get two eigenvalues from lambda 1 is 1. That's not a guarantee, though. We'll see some matrices which are defective. Just because the multiplicity is high doesn't guarantee the eigenspace has the same dimension. The dimension here can never exceed the multiplicity, but it can go below. Well, that's our wrap up of example 1. Any questions at all, folks? Finishing this one. Okay, well, what we want to do in these notes is continue to practice with the characteristic equation and also look into some connecting thoughts of what happens when the matrix is not defective. Look into a couple interesting theorems that takes us into section 5.3. So let's try out this all again with example 2. Compute the eigenvalues of a 2x2 matrix A. This one is the problem that's always going to be not too bad to solve by hand, because no matter how bad the characteristic equation gets, sometimes it's nice when it does factor, but even if it doesn't factor too nice, we still have the quadratic formula at your beck and call that we can use. So to find the eigenvalues of this one here, the reminder is we go immediately to the characteristic equation. First, let's write the polynomial. Determinant A minus lambda I means subtract lambda from the main diagonal and take the determinant of the result. So 1 minus lambda, 1, -3, and 2 minus lambda is the result we'll get. Then the determinant's pretty fast. As a 2x2, we'll take the main diagonal, 1 minus lambda, times 2 minus lambda, subtract the off diagonal, so subtract 1 times -3. Let's expand this out, then set it to 0. This is equal to altogether 2 minus lambda minus 2 lambda plus lambda squared plus 3. So we've got the lambda squared minus 3 lambda plus 5. 5 being prime doesn't give us a lot to work with if we're factoring using integers. So we'll hit this one with the quadratic formula, it turns out. Set it to 0 and go from there. Kind of weird, right? Feels like we're reviewing a lot of algebra in this section. We saw the fundamental theorem of algebra pop out. Now it's the quadratic formula. Let's write out a quick note. The coefficients go a is 1, b is -3, c is 5. And the solution to this equation are guaranteed. They're going to be lambda equals -b plus or minus a discriminant b squared minus 4ac, kind of relaxing math in a certain sense, divided by 2 times a. Not as intense as some things we've did in prior chapters. Let's work out this part next, the discriminant. B squared minus 4ac becomes -3 squared for a 9, minus 4 times 1 times 5 is 20, giving us a -11. And that might set off some warning signs so far. We have a square root of a negative number. But as far as eigenvalues come up, that's perfectly fine. That's an ordinary kind of situation. This will turn into the square root of -11, which is going to be equal to I root 11. So complex unit comes out of nowhere on this one. And now lambda is equal to negative of b, so that's a +3, plus or minus. Well, the plus or minus tells us this is really 2 eigenvalues altogether. I root 11 divide by 2. Kind of strange, but those are our eigenvalues. We have one from using the positive, another from the negative, and the matrix that had only real numbers, sometimes they do come out with complex valued eigenvalues. Any questions at all with what's going on with this one if it's a complex value eigenvalue? Okay, I think this is the first time in a real big way complex values come out. Eigenvalues just have that kind of issue. Eigenvalues could be either real or complex. And sometimes it's kind of nice to think about what does it mean about this matrix A if you got complex valued eigenvalues? To think about that, let's just take a quick break on this one to think geometrically what is going on with that matrix. This matrix is very, very different. It had one real number eigenvalue, and when it comes to polynomials, complex values always come up in conjugate pairs, no matter what. The conjugate pair is when you have the plus and minus. So one complex value implies another complex value immediately. So the fact that we had one real eigenvalue means the other one's guaranteed to be real as well. And when it comes to real eigenvalues, this is what's happening geometrically with these eigenvalues. There is a subspace, span U, such that matrix multiplication by any eigenvector in here, not that one, it's not an eigenvector because it's 0, it's just going to keep you trapped in this invariant subspace. Geometrically, that's all that's happening with this matrix A. But this one is a lot different. This one's a kind of rotation matrix. Your vectors here, whatever eigenvector you might pick, is going to rotate around as you multiply by A. It could also spiral out depending on the modulus of this eigenvalue lambda, or it can spiral inwards towards the 0 vector. Just depends on the size or modulus of this eigenvalue lambda. So essentially, if you get complex values, it tells you this is one particular kind of rotation matrix that you're dealing with here. Really, the big warning is this also comes up in the homework. It could come up in the exam. I don't think I would throw the quadratic formula at you on the exam. I'd want to focus mainly on the linear algebra topics. But if you do get something that is complex values somehow, some way on the homework, don't throw them away. Those are the real eigenvalues of the problem, and that's what we were looking for. Let's try the next concept next. Again, the major part of section 5.2's notes is just this concept. We use determinant A minus lambda I to construct or generate the eigenvalues, whether they're real or complex. But there's more going on to this. This is the part of the notes in section 5.2 that's trying to connect us to the next section, 5.3. First is a quick theorem. It tells us the determinant of a matrix A is equal to the product of the eigenvalues of A. And we might have suspected that already, because if we look into, say, jumping back to 5.1, the 5.1 is a good place to come back to think about this theorem. one of the last problems we solved, say this one, we were able to get the eigenvalues using theorem 1 of chapter 5. Theorem 1 of chapter 5 tells you if you have a lower triangular, upper triangular, or even a diagonal matrix, any kind of triangular whatsoever, the eigenvalues are just the entries on the main diagonal. But then back in chapter 3, it tells us at the same time, the determinant of a matrix A, if it's triangular, again, these same three types, doesn't matter what kind of triangular, even diagonal, the determinant is just a product of the main diagonal. So this allows us to start to suspect that the determinant and the eigenvalues are actually pretty closely related. This is not a proof, but it gives us a thought that that's a pretty good idea. The way you would actually prove it is just work with the characteristic equation. I'll leave it to you in the reading, since doing a big derivation right before a holiday just doesn't seem like a fun thought. So I'll leave that derivation of the next idea of this theorem right here to the reading for you folks. This just makes it seem plausible. So we have a new kind of relationship that we'd like to talk about with matrices. We talked about in a big way as well in section 5.1. Row reduction never ever is going to give you eigenvalues. If you do a row operation, almost guaranteed you've changed the eigenvalues of the matrix each and every time. But there is one kind of relationship that does preserve eigenvalues. It's the similarity transformation. You have to have two square matrices and a third invertible matrix P. We'll say a matrix A is similar to the second matrix B, the main two we were considering. If you can find that invertible matrix P, that allows you to write either this first equation, P inverse times A times P equals B. We actually saw this kind of stuff in chapter 2 when we were looking into matrix inverses and equations. Or if you can write a second equation, A is equal to P times B times P inverse, we'll say A is similar to B, and going from A into P inverse AP is called a similarity transformation. Similarity transformations are nice because these things do preserve eigenvalues. First thing we'll check though is what happens to the determinant. So just as a quick warm-up problem, thinking about this new concept, we'll do this example 3, showing similar matrices, in fact, have the same exact determinant. It goes even beyond that. So the next theorem will tell us it has the same eigenvalues at the same time. So row reduction doesn't give us eigenvalues, but similarity transformations are the one nice transformation that won't change eigenvalues whatsoever. So to think about this further, let's work through example 3. It says, show that if A and B are similar, let's start right here. When it says that statement, the very first thing we should say is, well, what is the definition? We'll say, since AB are similar, go to where the red dot is in the definition, there exists P such that P inverse exists, or we could say determinant P is not 0 if you prefer, just a invertible matrix theorem way to say it. And now go to this line, we can just rewrite A equals, I guess I'm going to this line, but either one will work. Let's go for this one down here. A equals P times B. Combine those thoughts, let me try again. P times B times P inverse. So we have an equation. Either one is going to satisfy this example 3. I went with the bottom equation. So either one of these equations work, and that's just the consequence of having an A and B similar. Next thing we want to show is the determinants now have to be the same. So we'll start by just taking the determinant of the left-hand side. Here's determinant A. And this takes us back to section 3.2. If we're taking determinant A, that means on our next line, we're taking determinant P times B times P inverse. But we have a lot of nice tools to handle that specific situation. Once I find them, there they are. We can break down a product of determinants in this kind of way. Determinant AB or PB P inverse, doesn't matter how many factors in the product, can be broken down like this. At the same time, when an inverse comes up, we can just say it's 1 over the determinant of that original matrix. So using both of these ideas at once, determinant A turns into determinant P times B times P inverse. Now using the factoring property, this is determinant P. Let me try again the determinant. Determinant P times determinant B times determinant P inverse. But this P inverse can be just thrown down into the denominator. So this whole thing is now equal to determinant P times determinant B divided by determinant P, now just thrown into the denominator. We get a cancellation right out of the gate on that. And notice this is allowed because if P inverse exists, determinant of P is not 0, so it does make sense. It can go into the denominator. The whole result is just now determinant B. So that's what we were trying to show. If we have a similarity transformation, just using properties of determinants, following this track of equalities, determinant A turns into determinant B. So similar matrices are interesting in a certain sense. We want a certain kind of similar matrix, though. This is what section 5.3 is going to be all about, connecting the things we're talking about with defective versus non-defective matrices. When the matrix in the middle is diagonal, that's one of the more useful similar transformations that we're going to be dealing with in the next section. Well, before we go to the next example, any questions at all, folks, about the new definition or the quick example below? Okay, taking this to our last concept for these notes, here's our example 4. Again, pretty short set of notes. We're not going to try to go very far into the next section, but we'll find a good stopping point that makes sense for section 5.3. So we'll have a repeat of we have a brand new theorem that tells us if we have n by n matrices, A and B, and they are similar, then they'll have the same exact characteristic equation and the same eigenvalues with the same multiplicities. So the last example tells us similar matrices have the same determinants. But theorem 4 is new. It's telling us similar matrices also have the same eigenvalues, the property we were hinting at. So similarity transformation turns out to be a pretty interesting one. And here's a matrix A, B, and P that we're going to work with to think about theorem 4. It can be shown that A equals P times B times P inverse. This is my way of saying you don't have to show it. That's a lot of work doing the matrix multiplication and the matrix inverse right here just to start it out. Then multiply those 3 matrices together. I'm pretty much just saying, trust me, if you did all that work, you'd get back to the original matrix A, which by the way is a complicated looking matrix, that thing there. If I was to try to find the eigenvalues of that, I'm going to get a degree 3 polynomial, and factoring that is not always really straightforward. The one at the very top of the notes was just a fluke because it kind of fell out in our lap in a fully factored form right away. When we went through that 4x4 determinant, it was even worse. But in general, factoring these things is not always easy. We saw the quadratic formula complex values coming out. So if I was just told, find the eigenvalues of that matrix A, that could be a really long and hard-fought problem. We'll get there. There's algebraic polynomial function tricks that can make this happen. But if we know that A equals P times B times P inverse, we can say the following. The matrix A is similar to B. That's important because if we have these are 2 similar matrices, then the above theorem tells us they must have the same eigenvalues. So the eigenvalues of the matrix A are the eigenvalues of the matrix B. That's just taking us back to theorem 1 in section 5.1 once again. Let me see if I have that loaded up. Yeah, here it is. And the great comment that was made in class, by triangular matrix, we're including upper triangular, lower triangular, and diagonal matrices. This is our diagonal matrix B on this one. So theorem 1 applies to this at the same time as well. So we can just go here. This is a diagonal matrix. So use theorem 1 of chapter 5. So finally connecting theorem 1 of chapter 5, theorem 4 of chapter 5, through the similarity transformation, the eigenvalues of A are lambda 1 equals 18, lambda 2 is 12, and lambda 3 is 6. Then, well, we did it, folks. We've computed the eigenvalues of A. A lot of other stuff was just available to us to make that computation happen. So really the gist is theorem 4 makes the eigenvalues apparent the moment we trust this is true. If you get really bored, you can work this out and double check, but it is the right relationship. A is formed by doing P times B times P inverse. There's actually more to this story. What about the columns of P? Well, because P inverse exists, here it is, P inverse. The columns of P are linearly independent. So that's interesting. They would form a basis at the same time. And for just an extra concept here, this wasn't part of the whole problem, so maybe I should use a pen that looks more like a comment. V1 equals 140. V2 equals 111. These are all coming from the matrix P. And V3 equals 031. These are the corresponding eigenvectors. That order is really important. 18 was the first eigenvalue, so the very first column, 140, gave us the first corresponding eigenvector of the matrix A. So we know even more beyond theorem 4. This is the content we're going to be looking into in chapter 5. Likewise, 12 was the second eigenvalue on column 2. Corresponding column 2 gave us the next eigenvector. So similarity transformations are giving us a lot of stuff, but this only works if you have a diagonal matrix. So that diagonal matrix is really super special. These three eigenvectors are automatically linearly independent, which is also kind of special in a way. We knew that because P is invertible, so we know it's independent. These vectors span. So these corresponding eigenvectors form an eigenbasis for R3. So everything in orange here is just an additional comment, but these are the things we're going to be exploring in the very next section. Any questions at all, folks, before we take a look into what's going on in that next section? Okay, we did it. This is the conclusion to section 5.2. As far as the homework goes, these are the ones that are going to be due after the break. But I'm thinking I'm going to push this due date so that I think we'll be finishing it on Tuesday when we come back on December 2nd. So a more realistic due date on 5.3 is going to be December 9. We'll take a look at it, see what's going on. Not with the goal of trying to race through it and finish this whole thing. So this is all about diagonalization, and that diagonal matrix we were looking at is a hint of what's going on here in this next section. We would like to take any matrix and somehow, some way, write out this specific similarity transformation. A equals a matrix P times D times P inverse, where that matrix D is a diagonal one. If you can do that, you'll not only know the eigenvalues of the matrix A, you can get the corresponding eigenvectors from either the P inverse or the P matrix here. So that's a really powerful concept. So to just practice some kinds of algebra you can do with this, if you have a similarity transformation with a diagonal matrix, it makes computations like these really fast to compute. A to the power of 10 of a matrix in general sounds like it could be a lot of work. But if we assume A equals P times D times P inverse, this is a pretty fast computation. So let's write out how this will go while we're thinking about the diagonalization here and what it's getting for us. We do have a diagonal matrix, 1, -1. And we can say that A equals, just copying this down for a quicker reference, P times D times P inverse. So if we square that matrix, that's just going to be A times A, which will be P times D times P inverse. Substitute again, P times D times P inverse. But A squared is a fast computation the moment you have a similarity transformation like this, because those two matrices are just going to turn into the identity matrix. P inverse times P cancels. You'll have D times D in the middle. And so that tells us A squared is just P times D squared times P inverse. So that looks like it's the relationship that we're interested in. A to the power of 2 just gives us a new similarity transformation where the diagonal matrix D has changed into D squared. Let's work it out again. A cubed, just to see if the pattern works. A cubed can be factored as A squared times A. Substituting in for A squared, we found it's P times D squared times P inverse. Substituting in for A, it's P times D times P inverse. But then we just get another pretty much the same kind of cancellation. The matrices D squared and D combine, giving us P times D cubed times P inverse. My claim is this would work for any power of n. We can kind of see what the pattern would look like. If we were going to prove that from scratch, it'd be a proof by induction if you've done those kinds of weird things before. Let's take for granted, rather than trying to verify proof by induction problem, that does look indeed like a power of 10 is going to be P times D to the power of 10 times P inverse. Our goal is to compute a power 10, which means we might have to compute P inverse, just depends on the problem. But D power of 10 is now the interesting one that we want to take a look into. Let's see what happens with that whole thing, D power 10. Well, any questions at the moment, folks? Just working out the powers of A. Okay, let's give this a try next. For D to the power of 10. We can work this similarly like we did with A, going A squared, A cubed, and so on. Take D times D, here's that diagonal matrix. It's 1, 0, 0, -1, 1, 0, 0, -1. And word of advice when you do these kind of multiplications, sometimes it's more about the pattern that we're going to see rather than just cranking up the numbers. So I'm going to write this in kind of a weird way, just for the sake of pattern recognition. I want to write out first, forgot to say that this one is D squared to start. So first it's going to be 1 times 1 plus 0. That would give us a 1 squared, which is obviously 1, but 1 squared for the sake of finding a pattern. Then it's going to be 0 plus 0 for an entry of 0 below. Then redo it again. We're going to be working with this column. This will be 0 plus 0 for a total of 0. And then 0 plus -1 times -1. So we have 0, -1 squared. That one's just the identity matrix with that power of 2. If we redo it again and go d cubed, this would be d squared times d. We've computed d squared to be 1 squared, 0, 0, negative 1 squared, multiply by the matrix D, and we get 1, 0, 0, negative 1. But you might already have a good idea of how this ought to go. Diagonal matrices are kind of nice because, as the pattern is going to reveal, any power of the diagonal matrix is just going to be the entries along the main diagonal raised to that power. So even if this was a 1, 7, d to the power of 10 would be 1 to the power of 10, 7 to the power of 10. But just for the sake of seeing that happen, let's work this out again. This is 1 squared times 1, so 1 cubed plus 0 for just a 1 cubed. Then it's going to be a 0 plus 0 for a 0. Here, working with that second column, we'll get 0 plus 0 for a 0 again. Then it's going to be 0 plus negative 1 to power 3. And that's all d cubed is doing. It's just operating whatever the power is on the main diagonal. So when you go to do this in the homework, it's actually pretty fast. You can just jump down to the big punchline, do this over and over again, and d to the power of 10 is just going to be the result of taking the main diagonal to that same power. So it's 1 power 10 here, 0, 0, negative 1 to the power of 10. That means it's the identity matrix 1, 0, 0, 1. We get I. But because we get I right here, our work is essentially done at this stage. This tells us a to the power of 10 is p times an identity matrix times p inverse. There's a cancellation in the middle. This is now just p times p inverse. So the whole thing turns into the 2 by 2 identity matrix. So we never even had to find out what a was in the very first place to get a power 10. We never did this original multiplication right here to reconstruct a. If we know a is similar to a diagonal matrix, any power of a is really fast to compute in this kind of way. Well, if it was an odd power, it would have been a little bit more work because we might have had, say, a 1 and a negative 1, not the identity matrix. Then you do have to find p inverse, then multiply all of it together. So it was kind of just fortunate it was an even power on this one, making it a faster problem. Well, any last questions, folks? Just working with the new idea, a diagonalizable matrix. Okay, well, here's our big theorem. Tying together similarity transformations, but using specifically a diagonal matrix, here's what we get when we put it all together. All the concepts from chapter 5 so far gives us the diagonalization theorem. Above is just the definition for easy reference. We say A is diagonalizable. That sounds like an abuse of the English language, but let's go with it. A is diagonalizable if it's similar to, so that's the P and P inverse for the similarity transformation, a diagonal matrix. So that's the diagonal matrix indicated by the variable uppercase D. So if it's diagonalizable, you can now use this diagonalization theorem that tells us a whole slew of important facts about the original matrix A. First, the matrix A is diagonalizable if and only if, first there's an n by n matrix, it has to have n linearly independent eigenvectors. And those were the thoughts we were exploring when we had a high multiplicity eigenvalue. We were wondering if the dimension of the eigenspace matched the multiplicity. If it doesn't, it won't have n linearly independent eigenvectors, and through the if and only if, it's not going to be diagonalizable. There's more to the story. There's like 3 paragraphs here. So if A equals P times D times P inverse with a diagonal matrix D, that's saying A is diagonalizable. This will happen if and only if the columns of P are linearly independent eigenvectors of A. And that's what we were hinting at in the last section, or the last problem of the very last section. This original P inverse contains, or the matrix P, each one you look at, contains the actual eigenvectors of the matrix A. The diagonal entries are the corresponding, respectively, to those same eigenvectors. and they'll form an eigenvector basis. So it's a lot of words all at once. Saying this theorem takes a lot of words, there's a lot of concepts altogether, but actually using it is really, really fast if A has already been diagonalized like this. So let's give this diagonalization here a look just to see what's going on. This one would make a pretty good exam question. This would be, say, a final exam topic because it's just a really quick concept check. Given that A is this matrix times this other matrix. But look at the entries here. Those entries match up exactly with those entries. The only difference is the inverse here. That means we have a similarity transformation. The matrix in the middle is diagonal, so we have A is diagonalizable. So this part right here tells us this is a P, D, P inverse. A is, let's say, diagonalized. It's not only diagonalizable, this whole partition, this factoring, is the diagonalization. So A is diagonalized in that kind of way. It asks what are the eigenvalues, but here they are. The theorem says the eigenvalues are the diagonal matrix, are the diagonal entries of the diagonal matrix D right here. So we're looking at the eigenvalues the moment we have A diagonalized in this kind of way. The corresponding eigenvectors of A, you can either look to this matrix or the one that has the inverse on it. I'll identify it in this kind of way. We'll state the multiplicity as well as the dimension of the corresponding eigenspace. So the diagonalization theorem is really just this as a punchline. This particular factorization tells us eigenvalues are lambda 1 equals 5, lambda 2 equals -2. So we have the eigenvalues. We also want the corresponding eigenvectors, so let's get that part in. Eigenvectors are, actually, let me write it this way. The corresponding eigenvectors go V1, this column right here, corresponding to that entry 5, so 1, 1, -3. V2 is 0, 1, 0. So when it says the corresponding eigenvectors, we need to list it out in this way. So somehow I know that you know lambda 1 has these two particular eigenvectors corresponding with it. Likewise, lambda 2 corresponds to only this one, 2, 0, 1, because -2 appears in the third column. So that's what we mean by the correspondence. So V3 equals 2, 0, 1. So the eigenvalues are those two, and V1, V2, V3 are the eigenvectors. It also says for each eigenvalue state its multiplicity, as well as the dimension of the corresponding eigenspace. So it's asking for a lot. Let's run through this second part right here. Lambda 1 equals 5. Well, 5 shows up twice in the diagonal matrix. That means this one has been repeated, and we can say it has multiplicity too. We also want the dimension of the eigenspace for lambda 1 equals 5, but we don't have to work too hard on that. If there's two eigenvectors, these are guaranteed to be linearly independent, and we can say the dimension of null a minus 2i. This part right here, null a minus 2i, is what we mean by the eigenspace, but there's two vectors, so we say that dimension is 2. Then do it again for the second one, lambda 2 equals -2. This one has multiplicity 1. There's only one eigenvector. It's automatically linearly independent as a set because it's not the zero vector. So it tells us the dimension of null a plus 2i. Hang on, I think I made a mistake here. Plus 2i makes sense right here, is 1. But I made a mistake on that -2. I think I was looking at the multiplicity of 2. It should be null a minus lambda 1, the value 5. Let's correct that right here. Null a minus the actual eigenvalue itself, 5i. Dimension's right, but we need to mention the right eigenvalue to tie the concept together. So there's a lot going on here with that diagonalization. It revealed the eigenvalues, it revealed the eigenvectors. It also revealed the dimension of every single eigenspace as well, all in one shot. So pretty nice theorem. Any questions or comments at all, folks, running through pretty much just the ideas of this theorem in example 2? Okay, so it's one of those theorems where it's fast to use if A has already been diagonalized. But then the theorem takes a little bit of time to actually work if the example looks like this. Diagonalize the matrix A, or explain why it's not possible. We'll do several kind of problems just like these, but this is where we're basically reviewing all of chapter 5 in one go. We need to find the eigenvalues. We need to see what their multiplicities are, find the corresponding eigenvectors, and if the dimensions of the null space add up to the size of the matrix, this is 2 by 2, so we want the dimension of the null spaces to add up to 2. It is diagonalizable, and then we write our answer in this kind of form. So these are pretty big problems. These take a lot of steps. That's why I think this is probably a good stopping point for us here in these notes. We could finish one more example, but I think that's hard to do on the last day right before a break. We'll come back a little bit more fresh after a well-deserved break on Tuesday, refresh the diagonalization theorem, and then move forward on actually diagonalizing some of these matrices. We'll do some 2 by 2s, we'll work on some 3 by 3s, and go from there, culminating in this characterization theorem for diagonalization at the very end. But we made it, folks. I think this is a good stopping point for us so we can really hammer these problems and do them well when we come back on Tuesday. This will be December 2nd, so that's kind of crazy in a way. Any last questions at all, folks, before we call it a day early? Okay, we'll have a relaxing break, folks. I'll see you all when it's December.
Here, these back for you. Okay. You want me to give you, I have one more done, you want me to give you right now, or? Sure, I'll take it. Yeah. My break is mostly a catch-up week on Monday, Tuesday, Wednesday, so, now. Should have been like 4.4, 4.5. Yeah. Yeah. Awesome. Thank you.